Hey everybody, we are back for the second part of the methods of integration video. Again, I know I haven't posted this handout, but what we're going to cover today should hopefully be briefer than the other video. We're going to talk about trig. There's really only two things that we indicate. Oh, let's go focus there. Sorry about that. We're going to look at trig integrals, which only cover a couple things as far as we're concerned, and then we're going to look at mixtures, which are either like trig and exponential, or x to a power and exponential, or x to a power and logarithm, or any kind of mixture of one of those four different types of things, where it's either log or a power of x, or trig, or exponential, meaning e to the x. That's why I don't like this language here, exponent problem, for that first part, because I think of it, when I think of an exponential function, I think of e to the x. Whereas exponent, I would rather use the word power. I should use the word power there as well. So that's on the agenda for today. So let me go here. So methods of integration. Part 2. It's still Co-17B. And it actually is the 20th, even though I know I labeled the other video as the 20th as well. That was yesterday, which is the 19th. So, oh, interesting. All right, let's go here. Yeah, so part 2, trigonometry. So there's really only a couple of things we encounter when we deal with trigonometry for this class, and really it's integrals where you have either powers of sine and cosine, or powers of tangent and secant. You can also have cosecant and cotangent, but So for example, if I asked what's the integral of cosine to the 5th x times sine of x dx, we can actually let u equal either one, but the better choice here is to let u equal the one that's raised to a higher power. So we're going to let u, and this is specifically in the powers of sine and cosine subheading. You're going to let u equal cosine here. Your du is going to be negative sine of x dx. Negative du is equal to positive sine of x dx. And if I start replacing things, this is going to end up equaling, well, sine of x is my negative du, and then that's going to be u to the 5th. So we're going to be integrating, I'm going to put the negative out in front, negative u to the 5th du. I should say negative integral u to the 5th. We integrate, we get negative u to the 6th over 6 plus c. We put back in u equal to cosine, and we're getting negative cosine to the 6x over 6 plus c. Typically, if both sine and cosine are raised to an odd power, you let u be the trig function on its own, not raised to that power, but the one that's raised to a higher power. Things are a little bit different if you have an odd and an even power. So yeah, I can put this in here. So we have the integral of, yeah, I'll do this. Sine squared x, yeah, cosine cubed x. We may not actually encounter this, which is why I'm not spending a whole lot of time talking about it. If you happen to have something like this, your best bet is to let u equal the trig function that is raised to the even power. So here we're going to let u equal sine of x. Here's the reason why. When you have powers of sine and cosine, you want to make a choice for u, so that after you've dealt with du, so the derivative of sine is cosine. Wait, I have a cosine x. I'm probably going to rewrite this so I can see a little bit easier. So I'm going to rewrite this as the integral of sine squared of x. Cosine cubed is cosine squared x times cosine x. The idea here is that once we have dealt with the dx part changing to du, the thing that we did not pick u to be equal to, in this case, we picked u to be sine, so we didn't pick u equal to cosine. We want an even power on the not u choice left over. Here's why. Sine squared is just going to be u squared. Cosine squared, it's kind of like a back substitution. I need to deal with that. So I'm going to point out that we have a trig identity. We know that sine squared x plus cosine squared x is equal to 1. And so I can solve for cosine squared x, which is equal to 1 minus sine squared x. But then I chose u equal to sine of x, so really cosine squared x is equal to 1 minus u squared. And that is what's going to get thrown in right there. So then I can rewrite my integral as the integral of u squared times 1 minus u squared du. Distribute the u squared before you try to anti-differentiate. So I keep scooting this up here. There's a limited desk space here. I would say tell me if I'm off screen, but obviously you can't. So distribute the u squared, I get the integral of u squared minus u to the fourth, and I anti-differentiate, get u to the third over 3 minus u to the fifth over 5 plus c, and that's equal to sine cubed x over 3 minus sine to the fifth x over 5 plus c. I don't think you, as far as I've seen, we haven't encountered really this type of integral in class. The only type we've encountered, whereas you've got sine or cosine to a high power, and then the other trig function to the 1 power. So the choice for you is pretty obvious. You pick the one that's raised to the higher power. So for example, you also think about if you were trying to find the integral of, I don't know, sine to the fourth x cosine x dx, there is an obvious choice for sine, regardless of whether the powers are even, or sorry, the obvious choice for u, regardless of whether the powers of sine and cosine are odd or even. Here it is clear we should let u equal sine, because the du is exactly going to be cosine of x dx. And so we're immediately going to get that dealt with, and then we're going to rewrite our integral as the integral of u to the fourth. We anti-differentiate, we u to the fifth over 5 plus c. Oh, let's make this one definite just for fun. Yeah, so actually, here's what I would do. If this were a definite integral, I would still start off with, so let's pretend, let me go back in time for a second here. Let's pretend that the integral started off by asking to do the integral from 0 to pi over 2 of sine to the fourth x cosine x dx. So then I made this choice. I would have also changed my limits of integration. I would have said, okay, if u is sine of x, well, if x is 0, u is going to equal sine of 0, which is 0. If x is pi over 2, u is going to equal sine of pi over 2, which is 1. So I normally would say if this was the integral from 0 to pi over 2, I would change the limits of integration and say this is the integral from u equals 0 to u equals 1. And then instead of getting u to the fifth over 5 plus c, sorry about that, I'm going to get u to the fifth over 5 from 0 to 1, which will be 1 to the fifth over 5 minus 0 to the fifth over 5, which is just 1/5. If you prefer, you could instead say, I don't want to do it that way. I don't like changing my limits of integration, so I'm going to switch back. So I'm going to get my antiderivative, which is u to the fifth over 5, and then I'm going to plug back in that u is equal to sine. So the antiderivative of this is really sine to the fifth x over 5. Or if you prefer, and you might prefer for plugging in sine of x raised to the fifth power over 5. The reason I point this out is really because I wanted to show you that this actually is the antiderivative of that. If you take the derivative of 1/5 times sine of x to the fifth power, the 1/5 hangs out. The derivative of something to the fifth power is 5 times your something to the fourth power, and then those 5s cancel, and you exactly get, I forgot something. I forgot the chain rule. I get 5 times my stuff to the fourth power times the derivative of my stuff, which is cosine, and then I get sine to the fourth x times cosine x, which is exactly the function I was anti-differentiating in the first place. Back to this, if you plug in the pi over 2, you get sine of pi over 2, which is 1 to the fifth over 5, minus sine to 0, which is 0 to the fifth over 5. And you get exactly the same answer as you did doing it that way. So again, I recommend changing your limits of integration if you're doing a u substitution that is a definite integral, but you do not have to. One more, actually two more with sine and cosine, because they are kind of important. These are some important integrals here. It's specifically these integrals that don't start off looking like they have sine and cosine. The integral of tangent and the integral of cotangent. So the integral of tangent is probably maybe worth memorizing, but certainly it's worth knowing how to do. So I replace tangent with sine over cosine. I make my choice for u. I'm always going to pick u equal to the thing in the denominator. So here we're going to pick u equal to cosine of x. The derivative of cosine is negative sine, so du is equal to negative sine of x times dx. I like to fix this and make this a negative du equal to positive sine of x times dx. And then I'm going to start replacing things. Well, sine of x dx is equal to negative du. Cosine of x is equal to u. So I'm really going to have the integral of negative du over u, which you might prefer to write as the negative one out in front and a 1 over u du. Either way is fine. But you have to know that the integral of 1 over u is natural log of the opposite value of u, just like you have to know that the integral of du over u is the natural log of the opposite value of u. The d part is just telling you what variable we're antidifferentiating with respect to. The integral part is telling us we're doing an antiderivative. So then we're going to get negative natural log of the opposite value of u plus c. Finally, plugging back in, we get negative natural log of the opposite value of cosine of x plus c. I'll tell you, this is one of the two correct ways of writing the integral of tangent. The other way of writing this is thinking of this as negative 1 times the natural log of the opposite value of cosine of x plus c, which is then equal to the natural log of the absolute value of cosine of x to the negative 1 power, right? Bringing that negative 1 up as the power in the thing in the natural log. And then finally, the reciprocal of cosine is secant. So people also write this as the natural log of the absolute value of secant of x plus c. And either ways writing it is considered correct because they are both correct. So just to kind of sum up here, the integral of tangent is either equal to the negative natural log of the absolute value of cosine of x plus c, or it's equal to the positive natural log of the absolute value of secant of x plus c. On your own, before you watch the next part of this video, you should try doing the integral of cotangent. The integral of cotangent, we're going to do the same sort of thing. We're going to write it as cosine x over sine of x. And then we're going to let u equal the denominator one more time. So u is sine of x. My derivative of sine is cosine. So du is equal to cosine of x dx. Things are working out great. There's our du. There's our u. So then we're going to rewrite the integral as the integral of du over u. Again, you don't have to leave it like that. It's not terrible, but some people really prefer to see it like this. And then the antiderivative of 1 over u is the natural log of the opposite value of u. Let's see. Then plugging back in what u is equal to, we get the natural log of the absolute value of sine of x. Let's see. Pardon me. Say two things here. I'll say one, the integral of cotangent of x dx is equal to the natural log of the absolute value of sine of x plus c. And although it would be correct, no one ever writes this in the alternative way. So it would be correct to say that this is equal to the negative natural log of the absolute value of sine of x to the negative 1, which is cosecant of x. But nobody ever writes that, so you don't need to know it. All right, the other thing with just straight up trig, where you only have trig functions and no other mixture thing like an x to a power or a natural log or a d to the x, is powers of secant and tangent. Again, I'm going to keep this part hopefully brief because I don't think you're really going to see it. Let's pretend we had the integral of, let me make a good choice here. Sure. Tangent squared x, secant squared x. So just like in the sine and cosine problems, powers of sine and cosine problems, for powers of tangent and secant, you should let u equal to either tangent of x or secant of x. No power associated to just tangent or secant. So for example here, if I made the choice to let u secant, which I will tell you right now is the wrong choice, here's what happens. The derivative of secant is secant x times tangent x dx. The problem here is that I have a secant squared and a tangent squared, so I can break this apart as I'm going to put a tangent x times a secant x, and then I still have a secant x tangent x. Still the same stuff, just written very differently. There's my du. There's my u, and then I have a tangent left over, and it's the tangent of x to an odd power, and I don't have a trig identity for that. So this was the wrong choice. Instead, what I should have chosen was letting u equal the tangent. If u is tangent of x, then my du, the derivative tangent, is going to be secant squared x dx. And then if I rewrite this, well, I can see automatically that my there's a cat in here now. Sorry, she's a little bit ornery in the morning. I would show her all to you, but she doesn't really like to be picked up. So in this case, our du is secant squared dx, and tangent squared is equal to u squared. This is going to be the integral of u squared du, which is going to be u to the third over 3, plus a constant, which is then going to be tangent cubed x over 3 plus c. Cool. I'm going to pause the recording for a second because maybe she needs some food. I'll be back momentarily. Not that you won't know. I'll be back instantaneously. Oops, that's pausing the screen sharing though. Yeah, there we go. There's usually a pausing the video option. There we go. Pause the recording. Okay. All right. The monster has been fed. Hopefully she will stop yelling. Let's do one more problem like this, and then we will move on to the mixture stuff. So you might see an interval like the following. Yeah, secant cubed x, tangent cubed x. Again, I'm not 100% sure you'll actually see something like this, but it's good to cover our bases. Let's make this one definite just for fun. So let's say we're going to go from, 0 to pi over 4. Why not? So for this one here, we're going to let u equal, again, you have a choice of tangents, so you can usually, sometimes either choice will work, but usually only one. Here, the correct choice is actually secant. Here's the reason why. If we picked u equal to tangent, our derivative would have been secant squared. After dealing with that, there would have been secant to the first leftover. And so our choice of u being tangent, the not u thing, there's an odd number left over, which is not good. On the other hand, for that u equals secant, our du is equal to secant x times tangent x times dx. Pulling out a secant x times tangent x, I'm left with the following. Secant squared x, I pulled one out. Tangent squared x, I pulled one out, and then I have the secant x, tangent x. I'm not really pulling them out, I'm just like pulling them to the side here. Still the same thing, secant squared times secant cubed, tangent squared times tangent is tangent cubed. But then, there's my du. U is equal to secant, so secant squared is just u squared. And then the not u choice, so in this case, the thing I didn't pick for u was tangent. There's an even power of tangent left over. And then we get to use our favorite trig identity, I tan, and get sexy. Or in this case, solving for tangent squared x equals secant squared x minus 1. But u is equal to secant of x. So we're going to sub that in down there, or not sub, sure, yeah, sub. So tangent squared x is equal to u squared minus 1. So then we're going to get the integral of u squared times u squared minus 1 times du. We might as well change our limits of integration as well. So if x is equal to 0, u is equal to secant of 0. Secant is 1 over cosine, so it's going to be 1 over cosine of 0, which is 1, because cosine of 0 is 1. And if x equals pi over 4, u is going to equal, let's just write it as 1 over cosine of pi over 4. Cosine of pi over 4 is 1 over root 2, or root 2 over 2, but I'm going to write it like that, so then I can see that secant of pi over 4 is just equal to root 2. And then we distribute the u's. Take the integral from 1 to root 2 of u to the 4th minus u to the 2nd. Then we plug in and we get we anti-differentiate. We get u to the 5th over 5 minus u to the 3rd over 3 from 1 to root 2. We should have picked a different number, but well. And then that's going to end up equaling the square root of 2 to the 5th over 5 minus the square root of 2 to the 3rd over 3 minus 1/5 minus 1/3. And I would not try to make this simplified. I would just leave it like that. That's it. So powers of sine and cosine, powers of tangent and secant. If you are faced with those, your goal is to make a choice for u so that if there are leftovers of the not u thing, you have an even power of them left over. But again, probably not going to see that. So yeah. All right, let's get into the more important part here, which is the mixtures. I'm going to put it on the ground over here. So mixtures. I guess this would be like part 3. Mixtures. So when faced with, and so let's just write out a bunch of types of mixtures before we get too into it here. Let me see here. Notes real quick. I like that. So there's, again, mixtures. Typically, I will say mixtures of logarithms. So logs, like natural log of x. That's mostly what you're going to see. You could see a log with a different base, but that's unlikely. So really, I would say natural log of x. I suppose you could see something like the natural log of 3x or the natural log of x squared. And at both of these cases, before you do anything else, you should simplify this as the natural log of 3 plus the natural log of x, or this as 2 times the natural log of x. Algebra or any power of x. So people call this an algebraic term, or just, I like to say any power of x. So really that's a lot of things there. That's like, x to the 5th, x to the negative 3rd, the square root of x, because that's x to the 1/2. You can also have like x plus 2 to the 7th. All these qualify. Those are all algebraic things as far as we're concerned. We're talking about mixtures. You could have trig, and really that's any trig function, right? Sine, cosine, tangent, cotangent, secant, cosecant. You're most likely to see those ones. You're less likely to see cotangent, cosecant, but it's not impossible. And finally, exponential, or as you might think of it, e to the x. So things like e to the x, e to the 2x, e to the x squared, etc. Anything like that, that's an exponential thing. I will say e to the x squared is an example of a mixture of an exponential and an algebraic thing, because the x squared there is also kind of considered to be an algebraic thing. So we're looking for essentially a combination of 2 of these things, a log and an algebra, a log and a trig, a log and an exponential, or an algebra and a trig, or an algebra and exponential, or trig, and right? Those are kind of the list of combinations. So let's look at, let's start off with something like, and really you can kind of do whatever. So when it comes to mixtures, really there's 2 questions you're going to ask. Does it look like a U sub? Meaning, is there a good choice for U so that the derivative of that is also there? Is there a choice for U so that the derivative of U is there? For example, the integral of 3x squared e to the x cubed. Definitely a mixture, but there's a really good choice for U. Letting U equal x cubed, my derivative of x cubed is exactly 3. I probably could have not written the 3 there and just said x squared, but either way, the derivative of x cubed is 3x squared. So that's an excellent choice for U. Or, I should have probably written this on the next page for a while. If that's not the case, so if not, then the only other thing we really have is integration by parts. Then try integration by parts. So for example, if my integral was, say, the integral something like x squared times e to the x, that's not a good choice for you here. We can't, you might think, oh, James, I see an x squared and the derivative of x squared is 2x. In fact, I could even try to be a little more trickier into that, but that's not a good choice for you. If u is equal to x squared, if I was trying u substitution, my du would be 2x. But the problem is, you don't have a 2x times dx, right? That 2x there is stuck inside the exponent. So here, u sub is not the way to go. Instead, we're going to do integration by parts. Now, I'll point out that for integration by parts, I'm going to make the same choice for you. Right? For integration by parts here, I would let u equal x squared. My du would be 2x dx. I usually write the dv over here, sorry. Sure, let me write that over. U is x squared. Du, it doesn't really matter where you write it. I'm just used to writing it this way. And then dv is everything else. So once you've picked what u is, everything else has to be dv. So dv is e to the 2x dx, and v is e to the 2x divided by 2. And then we would do the integration by parts, we would get uv, x squared times 1/2 e to the 2x, minus the integral of v du, which is 1/2 e to the 2x times 2x dx. 2's cancel. We have x squared 1/2 e to the 2x minus the integral of x e to the 2x, and oh no, we have to do integration by parts again. So now for this new integral, let's do it in red. Our u is going to equal x, our du is going to be 1 times dx. Our dv is the rest, which is e to the 2x dx. And v, once again, is 1/2 e to the 2x. So then we're going to get this part still there. I'll put the 1/2 out in front. 1/2 x squared e to the 2x minus the integral of this is going to be, well, it's going to be u times v, x times 1/2 e to the 2x, minus the integral of v du, which is the integral of 1/2 e to the 2x dx. Writing this out, you get 1/2 x squared e to the 2x minus 1/2 x e to the 2x minus is plus the integral of 1/2 e to the 2x is 1/2 e to the 2x over 2, or 1/4 e to the 2x. I feel like I might have missed a fact. No, I guess it didn't. Yeah, that makes sense. Okay. Yeah. So just to point out this, plus c, of course. I will point out for this particular type of mixture problem, you could have done tabular integration as well. So it's kind of line here. And again, just as a tabular is just a specific way of doing certain integration by parts problems. If you had wanted to do this one using tabular, what we would have done is said, okay, tabular. What you do is you say, okay, well, my choice for u is x squared. My choice for dv is everything else. I'm not going to write the dx though. And then I take the derivatives here. So derivatives. Derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. You should get down to 0 if you're doing tabular. Antiderivatives, you get 1/2 e to the 2x, 1/4 e to the 2x, 1/8 e to the 2x. And then we do plus that times that, minus that times that, plus that times that. So our answer ends up being x squared times 1/2 e to the 2x minus 2x times 1/4 e to the 2x plus 2 times 1/8 e to the 2x plus c, which simplifying is 1/2 x squared e to the 2x minus 2 times 1/4 is 1/2 x e to the 2x. 2 times 1/8 is 1/4 e to the 2x. Which, if we look back, is exactly the same answer as we got doing it the long way. So if you see something that looks like the integral of x to a power times e to the something times x, or this also works for like the integral of x to some positive integer power times cosine of some multiple of x, or x to some positive integer power times sine of some multiple of x. The reason this works for these in particular and nothing else is because if you have x to a positive integer power, eventually the derivative, if you keep doing it, will be 0. And if your dv part is cosine or sine, the antiderivatives of cosine and sine just cycle, just like e to the 2x is really kind of the same thing over and over and again. They don't get more complicated. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. You just kind of go through the cycle. So just as a quick example of this again, if I said I wanted to integrate, say, x cubed times sine of x, let's make it sine of, I didn't know there was a little room there. Let's make it sine of 6x just to make it gross. Sorry, I know. It's a sine of 6x. So I would let u equal x cubed, and then the derivatives are 3x squared, 6x, 6, and 0. My dv is going to be sine of 6x. The antiderivative is negative cosine of 6x divided by 6, so negative 1/6 cosine of 6x. The antiderivative of that's going to be negative 1, 6 times 6 is 36 sine of 6x, right, and dividing by another 6. The antiderivative of negative sine is positive cosine, so it's going to be 1/6 cubed times cosine of 6x. And finally, the antiderivative of that's going to be 1/6 to the 4th times sine of 6x. So then the integral is going to equal, let's do it this way. Plus that times that, minus that times that, plus that times that, minus that times that. So plus x cubed times negative is going to be a negative 1/6 x cubed cosine of 6x. Minus a minus is a plus, it's going to be plus 3 divided by 36 reduces to 1/12 x squared sine of 6x, plus 6 divided by 6 cubed reduces to 1/6 squared, which is 1/36 cosine of 6x. 6/6 to the 4th reduces to 1/6 cubed, which is 1/216. So we get minus 1/216 times sine of 6x plus c. And although it's kind of gross, it's a lot less gross than doing integration by parts the long way 3 times. So tabular integration. Let's get back to the bigger picture here, which is talking about just mixtures. So we can talk about mixtures forever. I don't intend to, though. So let's look at a few examples and then we'll call it a day. Let's look at the example of, sure. What did I have in mind here? Yeah. The integral of something like x times secant squared of x squared plus 6. It's a mixture. You've certainly got x to a power times secant squared, so an algebraic term times a trigonometric term. And really, when you see a mixture, you should first think of u substitution. Can I do a u sub? U sub is usually easier. So I'm going to see, well, the only seemingly logical choice for u would be to let u be the stuff stuck inside the trig function. So u is going to equal x squared plus 6. Is the derivative of that also in my integral? Yeah. I've got an x times dx. I don't care about the 2. So I'm going to say that 1/2 times du is equal to x times dx. If it's helpful, you can rewrite the integral. You might also just say like, oh yeah, look, I can circle this in the weirdest way possible and say that that part there, x times dx, is equal to 1/2 du. If you don't like that, and I kind of don't like that, you could also just rewrite your integral, moving the x to over there. So you've got secant squared of x squared plus 6 times x dx. And then you're like, oh yeah, that's my 1/2 du. X squared plus 6 is my u. I'm going to rewrite the integral as the integral of secant squared of u times 1/2 du. You should just get in the habit of pulling that constant multiple out in front of your integral. So I should have just skipped that step and gone straight to saying it's 1/2 the integral of secant squared of u du. We do have to know that the antiderivative of secant squared of u is tangent of u. The derivative of tangent of u is secant squared. The antiderivative of secant squared of u is tangent of u. So this is going to end up equaling 1/2 tangent of u plus c. We did the integral, so we no longer write the integral symbol, right? We did what the instructions told us to do, and this said anti-differentiate. Finally, plug back in what u is equal to, and we get 1/2 tangent of x squared plus 6 plus c. Versus, I mean, I had an example in mind here, and I have to think about what it was. What was it? Yeah, I think it was just the integral of x times secant squared of x. Now there is not a good choice for u. We definitely, for u substitution, there's not a good choice for u. You would never let u equal x in a u substitution, because that's just changing all the x's to u's, but the integral is still the same integral. And letting u equal secant or secant squared, like if u was secant, my derivative is secant tangent. I don't have that. If u was secant squared, that's even worse. My derivative is 2 times secant tangent. I definitely don't have that. U sub is not a good way to go. So usually, again, when you're thinking U sub, you're thinking, is there some inside part of some other function that's a good choice because its derivative is also there? I don't have that here. So instead, I'm going to look towards integration by parts. And looking at my late acronym, I should pick U to be the first thing in this list. I don't have a logarithm. I do have a power of x. So U is going to equal x. dv gets to be all the rest. dv should be something that is easy to anti-differentiate. The derivative of u equal to x is just 1 times dx. And the antiderivative of secant squared, as we just saw, is tangent of x. So I'm going to rewrite this integral as the integral of x times secant squared of x dx as u times v minus the integral of v du. And we just did the integral of tangent a page or two ago. The integral of tangent ended up being the negative natural log of the absolute value of cosine of x. Or you could do the work again of writing a sine over cosine and doing a u sub. So sometimes when you do integration by parts, you also then get to do a u sub. So that's going to be x times tangent of x minus the negative natural log of the absolute value of cosine of x. You could have also written minus the positive natural log of the absolute value of secant of x. Either way is correct. I chose the minus one here because I knew the minus signs were going to cancel out, and I kind of like that. So minus plus the natural log of the absolute value of cosine of x. Let's see. So integration, a little bit of words. U sub versus integration by parts. U sub, we saw a good choice for u, whose derivative was also there. Integration by parts, we saw, U sub, we saw a mixture of things, but a good choice for u. Integration by parts, we saw a mixture of things. We did not see a good choice for u. That's really kind of the prime difference between u sub, for mixture problems, between u sub and integration by parts. Do you see a good choice for u, for a u sub, or do you not? Let's look at a couple more examples and then we'll try to wrap it up here because we are already, I don't see my timer up here. We're already like 50 minutes in, so I should try to finish this up pretty quickly here. I'm not going to get to area between curves. I'll have to save that for Monday. So a couple more here and then we will call it. So let's look at something, try and hit all the kind of the big examples here. So like, for example, the integral of the natural log of x to the 5th over x versus the integral of the natural log of x over x to the 5th. They look kind of the same. They're not the same, obviously, but they look similar. And let's make these both, definite integrals. So let's say they're going to be integrals from, oh, but we'll try to cover some improper stuff at the very end, though, just to kind of talk about that. So let's say this is the integral from 1 to e. This is also the integral from 1 to e. For integrals that are definite, that have like a lot of crap going on, sometimes I just like to do the improper, the indefinite integral first. So let's look at this one first. So over here, again, just looking at the indefinite integral because I don't feel like thinking about changing my limits of integration and any of that jazz. Also, I don't know if I'm going to have to. Here, there's definitely a u sub possibility. I can let u equal the natural log of x. My du is 1 over x dx. And I exactly have a 1 over x times dx. If you prefer, it is totally okay to rewrite this as the integral of the natural log of x to the 5th times 1 over x dx. And it's easier to see, oh yeah, that's my du, and there's my u. So this integral becomes the integral of u to the 5th du. Then after we have changed from x's to u's, you still have to do the antiderivative. So then we're going to get u to the 6th over 6 plus c. I don't really need the plus c here because it's a definite integral. But if I was still finding the, I'm going to write it for now. If I was finding the antiderivative, I would get the natural log of x to the 5th over 5 plus c. Now, going back to actually answer the question, and again, I know it's a u7, normally I would change limits of integration. I decided not to this time. So then I would go back and write the integral from 1 to e of the natural log of x to the 5th over x. Well, I already know what the antiderivative of that is. It's the natural log of x to the 6th, although somehow I wrote 5s here because I'm not paying attention. It's clearly too early in the morning. Sorry about that. This would be the natural log of x to the 6th over 6. I would then just say, okay, well, I know the so using the fundamental theorem of calculus part 2, the definite integral of some function is the antiderivative of that function evaluated at your endpoints. So we're going to get the natural log of e to the 6th power over 6 minus the natural log of 1 to the 6th power over 6. And we should simplify that because the natural log of e is 1, and 1 to any power is 1. And the natural log of 1 is 0. And 0 to any positive power is 0. So we end up just getting 1/6. Cool. For u substitution, I usually recommend changing the limits of integration, but I didn't know it was going to be u sub when I started off, so I was just kind of doing it. But this other problem, I do recommend the same sort of idea. I don't like doing definite integrals when it's complicated, when it's an integration by parts or some other terrible process like long u sub. So I'm going to see, well, I don't have a good choice for u here. Oops, sorry. If I picked u, sorry, there's a stray mark there, apologies. If I pick u equal to natural log of x, the du is 1 over x. And while I have that, there's still going to be an extra left over x to the 4th. This is definitely a situation where integration by parts is the right call. We should still make the same choice for u, but then the dv has to be everything else, which is 1 over x to the 5th times dx. Right? When you're thinking integration by parts, you're thinking these two pieces should multiply to the entire thing. And the natural log of x times 1 over x times dx, sorry, 1 over x to the 5th times dx is all of that. And then my du is 1 over x. And I should really write this as x to the negative 5th dx, so that it's easier for me to anti-differentiate. My v is going to be x to the negative 4th over negative 4. So then just doing the indefinite integral, the integral of natural log of x over x to the 5th dx is equal to u times v, natural log of x times x to the negative 4th over negative 4, minus the integral of v du, which is x to the negative 4th over negative 4 times 1 over x. Oh, I forgot the dx there. We should really simplify this to make our lives easier. So I'm going to rewrite this as, let's put the next to the negative 4 in the denominator is x to the positive 4. So I rewrite this first part as negative natural log of x over 4 times x to the 4th. And the negative 4 became a negative 4. And the x to the negative 4th in the numerator came down as x to the positive 4th in the denominator. Similarly here, I'm going to pull out a negative 1/4. So negative negative is positive 1/4. And then I'm going to have the integral of x to the negative 4th divided by x. When you divide two powers of x, you subtract their powers. Negative 4 minus 1 is negative 5. most of the time when you have a logarithm, a natural log of x, and then your dv is like some power of x, after you do this process, you end up with a new integral that's kind of almost the same as the choice you made for dv. That's very common. You do have to simplify this though before you integrate. And then we're going to get a negative natural log of x over 4x to the fourth plus 1/4. The antiderivative of x to the negative fifth, we kind of already did it. It's x to the negative fourth over negative 4. And then if I was actually writing this out, I would write it out as the negative natural log of x over 4x to the fourth minus 1/16. 1 over 16x to the fourth, because that x to the negative fourth, I'm going to bring down to the bottom. And 4 times negative 4 is minus 16. It's 16. Yeah, it's, yeah, let's see. So then, back to the actual integral, the integral from 1 to e of natural log of x over x to the fifth dx. I'm just taking the antiderivative of that, which is all of this. So negative natural log of x over 4x to the fourth minus 1 over 16x to the fourth. I could get a common denominator here, but I don't really think we need to. It seems unnecessary to me. And then we plug in. We get the negative natural log of e, which is negative 1 over 4 times e to the fourth minus 1 over 16 times e to the fourth minus, then we plug in 1. The negative natural log of 1 is going to be 0 over 4 times 1 to the fourth. Oh, there's my cat again. Minus 1 over 16 times 1 to the fourth. Oh my god. Goodness. Okay. And then small simplifications, that's 0. That's 1. So I would rewrite this as, I don't want to do too much rewriting here, so I'll just rewrite it as negative 1 over 4 e to the fourth minus 1 over 16 e to the fourth minus a minus is plus 1/16. And that's where I'm going to leave that. I'm going to take another pause and help this cat out here. I always pause the screen sharing, but let me pause the video for a second. Okay, so let's do a couple more of these. So let's do a couple more like distinguishing between what you would do when, and then we will talk about improper for just a minute. So, for example, if you had something like this, x cubed times cosine of x, this is an integration by parts problem, and specifically repeated. This is definitely a, that's what I'm looking for. Wow, a tabular method, tabular IDP, versus the integral of x cubed times cosine of x to the fourth. That's definitely a u substitution. You would let u equal x to the fourth. D would be 4x cubed dx. 1/4 du would equal x cubed dx. This integral, so there's my 1/4 times du. There's my u. So this integral becomes cat 1/4 times cosine of u du. Go away. And then that's going to be 1/4. The integral of cosine of u is sine of u. And then we get 1/4 sine of x to the fourth. I don't know what you're doing. Here's my cat. She is black. Stop. Okay, so there's one other thing I wanted to look at. Oh yeah, the one other integration by parts thing. So we've dealt with most, but yeah. The one other thing I should say you need to be on the lookout for is you might get asked something like the integral of sine of x times e to the 3x, for example. When you see something like this where it's either sine or cosine times e to the something times x, and it could be sine of 2x or cosine of 3x or whatever, this is an integration by parts twice, and then you have to get back what you started with. So here, we're going to let u equal sine of x. dv is the rest. du is cosine. V is the antiderivative of e to the 3x, which is 1/3 e to the 3x. We rewrite this as equal to u times v. Minus the integral of v du. I like to simplify this a tiny bit by bringing out the 1/3. This is equal to the 1/3 from the integral specifically. So you got 1/3 sine of x times e to the 3x minus the integral minus 1/3 the integral of cosine of x times e to the 3x dx. And now we do integration by parts again for this, and we make the same type of choice, meaning before we let u be the trig thing and dv be the exponential thing. So we're going to make the same choice here. We're going to let u be the trig thing. dv is going to be the rest, which is the exponential thing. du, the derivative cosine, is negative sine of x dx. V is the same as it was before, 1/3 e to the 3x. Yeah, hopefully she can be quiet. So then we're going to get 1/3 sine of x times e to the 3x minus 1/3 times the entire integral of this, which is uv minus the integral of v du. So uv, so cosine x times 1/3 e to the 3x. Hopefully I left myself enough room here. Minus the integral of v du, which is, I did not leave myself enough room. I poorly judged here. 1/3 e to the 3x times negative sine of x. Sorry, I'm scrunching that in. I know it is terrible. Let me distribute. So I'm going to write this, right? Here's what we're starting with. The integral of sine of x times e to the 3x dx is equal to this 1/3 sine of x times e to the 3x minus 1/3 times 1/3 is 1/9 times cosine of x times e to the 3x, and then minus 1/3 times a minus 1/3 times a minus times a minus times a minus is a minus. That's a minus 1/9 times the integral of sine of x times e to the 3x dx. But look, this integral is the same as the integral we started with. So we're going to add a 1/9 integral of sine of x e to the 3x to both sides. And this is a very typical process. So then you have 1 of something, or 9/9 of something if you prefer, plus 1/9 of something. So what we end up getting is 9/9 plus 1/9 is 10/9 of that integral of sine of x times e to the 3x dx is equal to all this right there. I'm really hoping I can fit this in on this page because it would just be nicer if I could. And then finally, to multiply both sides by 9/10, we get that the integral of sine of x times e to the 3x dx, and I would just put you could distribute the 9, but I'm just not going to because I'm out of room. You get 9/10 times, I don't know why I put, I made a little mistake there. That shouldn't be cosine of e to the 3x, that should be cosine of x times e to the 3x. That is terrible, I am sorry. Oof. So 1/3 sine of x times e to the 3x minus 1/9 cosine of x times e to the 3x, and then plus c. That's how you do a problem like that. It's a little bit gnarly, but that's what it is. So not that we've exhausted every type of mixture, but that's kind of the idea, right? If you've got a trig times a x to a power, or an e to the x times x to a power, or stuff like that. It might be a mixture, it might be an integration by parts, I'm sorry, it might be u substitution, it might be integration by parts. You kind of have to just practice. But when you see mixtures of things, you should first look for a good u substitution, and then if you don't see one, then move on to integration by parts. All right. The last thing I'll say, and this is not a method of integration, this is a type of integral. So all the methods are how you do the antiderivative. Whereas if you're faced with something like the integral from 0 to infinity of x times e to the negative 2x, that's still a mixture problem. The actual integral here is going to be integration by parts, the process for doing it. But before we can do any of that, we have to recognize that this integral itself is improper. It's a definite integral. Every improper integral would have to have been definite. So you can't, the only way you're improper is if you have limits of integration, which are definite integrals. So we're going to start off by writing this as the limit as b goes to infinity of the integral from 0 to b of x e to the negative 2x. Now, to do this, we're going to do, and this is where I really recommend doing the indefinite integral on your own. The indefinite integral from, of x e to the negative 2x is just integration by parts. We're going to let u equal x, dv is the rest, du is 1 dx, v is e to the negative 2x divided by negative 2. Rewriting this, it's going to equal u times v minus the integral of v du. I do recommend writing things with positive powers. Yeah, positive powers, generally. So I'm going to rewrite this as negative 1/2 times x over e to the positive 2x minus a minus is plus 1/2 the integral of e to the negative 2x, which is going to end up being negative 1/2 x over e to the 2x plus 1/2. The integral of e to the negative 2x is e to the negative 2x over negative 2. I don't really need the plus here because this is just kind of side work. And I'm going to simplify this one more step. I'm going to rewrite this as, yeah, it's fine. So I'm going to write this as negative 1/2 x over e to the 2x minus 1/4 times 1 over e to the 2x. So then, doing this, we're going to have the integral from 0 to infinity of x e to the negative 2x is equal to the limit as b goes to infinity of the integral from 0 to b of x e to the negative 2x dx. And then I know the antiderivative of this is just that. So that's going to be the limit as b goes to infinity of, some people like to factor out the 1 over e to the 2x, and I can kind of get on board with that, I guess. So if I factor out a 1 over e to the 2x, I'm left with a negative 1/2 x minus 1/4 from 0 to b. And actually, I'm going to write that in the numerator because I really want to think of this as a fraction. So write this as the limit as b goes to infinity of, if I plug in b, I get negative 1/2 times b minus 1/4 over e to the 2b. Minus, if I plug in 0, I get 0 minus 1/4 over e to the 0. And now here's where this is a little bit challenging. This part here, normally you'd have to use L'Hopital's rule to show what the limit is, because if you plug in infinity, you've got a negative infinity over infinity. This is just going to be 1/4 over here. So you could use L'Hopital's rule and say that the limit of this part is really the limit as b goes to infinity of the derivative of negative 1/2 b minus 1/4 is just negative 1/2. The derivative of e to the 2b is 2e to the 2b. This here, I'm not using L'Hopital's rule on that part because it's just a constant. I'm just going to say I have a plus 1/4 over here. And then you have a negative 1/2 divided by something that's getting infinitely large, so that limit's going to equal 0. Plus 1/4. So that's going to converge to 1/4. The other way of dealing with this is by saying, well, the bottom thing's an exponential thing, the top thing is just a power thing, and this is going to grow way faster, so this whole thing is going to get smaller and smaller and smaller, which is going to go to 0. That's how we deal with that. So, and just to point out, improper integrals don't have a certain method attached to them. You might need to use integration by parts. You might need to use partial fractions. You might need to use u substitution. It really just depends on the kind of integral. Let's look at one more, and then we will call it a day. So let's say, for example, I wanted to find the integral from 1 to infinity of x over x squared plus 1. So I will point out we have to do a u-sub here. It's not just arctangent because it's not 1 over x squared plus 1. So here we would do a u-sub. We would let u equal x squared plus 1. My du would be 2x dx. 1/2 du would equal x dx. I really can't stress enough. I do not like changing my limits of integration when it's going to be an improper integral. I know you could, right? If x is 1, u is 1 plus 1, which is 2. If x is infinitely large, u is infinity squared plus 1. I don't love doing that with infinity. So personally, I would do the following. I would do my indefinite integral off to the side. The integral of x over x squared plus 1 is just going to be, well, there's my 1/2 du, there's my u, so the integral of 1/2 du over u, or if you prefer, 1/2 times the integral of 1 over u du, which ends up being 1/2 natural log of the absolute value of u, plus c, which is 1/2 natural log of the absolute value of x squared plus 1. Let's see. You don't really need the absolute values anymore because x squared plus 1 is always greater than or equal to 1, but it's fine. So then doing the correct thing here, this is going to be the limit as b goes to infinity of the integral from 1 to b of x over x squared plus 1. And now I know the antiderivative of that is just that. So I jump straight to saying this is going to be the limit as b goes to infinity of 1/2 the natural log of the absolute value of x squared plus 1 from 1 to b. Plug in the limits of integration. You get the limit as b goes to infinity of 1/2 the natural log of the absolute value of b squared plus 1, and you don't really need the absolute value, but whatever, minus 1/2 the natural log of 1 squared plus 1. And then as b gets really large, b squared also gets very large. B squared plus 1 is also getting infinitely large, and the natural log of a number that is infinitely large is also getting infinitely large because the natural log function, you should remember on your right hand, looks like that, and as the x's get bigger and bigger, the y's get bigger and bigger. Right? Remember your right hand thing where that sorry, my hand's not the best, but that kind of looks like the natural log graph, and that kind of looks like the e to the x graph for your right hand. Make sure you're looking at your right hand. So then this is going to be infinity minus, it doesn't really matter, which is infinity. So this integral diverges. And technically you could say it diverges to infinity if someone asked, but hopefully no one's asking. All right, that is all I've got for you. I hope you all have a lovely weekend. Watch these videos, skip the parts you think aren't relevant. And I know it's great to say that at the end, skip the parts you think aren't relevant if you've watched it all already. But anyway, I will, yeah, I'll see you all on Monday.